So the last video in this module will be much shorter. We're going to talk about sources of carbohydrates for metabolism and then how those are then integrated into the TCA cycle and electron transport chain. We're going to briefly hit on beta oxidation and then finish it out with a concept of how efficient metabolism is. So what are sources for carbohydrates? We have two sources that are pretty common that I'm going to focus on here. The first is the Cori cycle. The Cori cycle is kind of a cool cycle that I'll show you a picture next, but the idea is that it produces glucose from lactate even at rest. Indeed, we have resting lactate in our blood. We have a resting lactate concentration of about 1 millimolar at rest. This lactate comes from skeletal muscle predominantly, a little bit of other tissues. Again, it is the byproduct of maybe we don't have enough oxidative metabolism going on, and so we shuttle pyruvate into lactate by lactate dehydrogenase into lactate to help recycle NADH into NAD. That can then be exported out of the tissue, transported by the blood to the liver, where it has the specific enzymes needed to synthesize lactate into glucose. So we can take a byproduct of glucose metabolism and turn it back into glucose itself, which I think is a pretty cool system. It can then use this to maintain blood sugar or to be stored in the liver as liver glycogen to be used later on when you are low on blood glucose. The other theory is the lactate shuttle hypothesis. This was proposed by a gentleman by the name of George Brooks, who's really famous in the field of exercise physiology. And he says that not only can we send it to the bloodstream, but if we have muscles nearby that are happy to use lactate, then we can use it in nearby tissues, including skeletal muscle, to synthesize glycogen, so convert it back to glucose and into glycogen, or we can take it back to pyruvate. You'll remember from the last module that LDH, lactate dehydrogenase enzyme reaction that converts pyruvate to lactate, is the same enzyme that can convert it back from lactate into pyruvate. And then once it is in pyruvate, it's then free to undergo oxidative metabolism again. Therefore, our view on lactate has changed quite a bit. So now, thanks to George Brooks, we do not view lactate as a waste product, but in other words, a way to shuttle glucose or really carbon backbones, right? Carbon backbones are the important part of this. We can use those carbon backbones to then create energy around the body. So what does that look like in one figure? So if we take a look at what this looks like, first we'll start with the Cori cycle. So during a high-intensity exercise or a situation where our oxidative metabolism is not able to keep up and we rely really heavily on anaerobic metabolism, glycolysis specifically, glycogen or glucose is broken down by glycolysis into pyruvate. If we don't have enough ability to shuttle that pyruvate then into mitochondria, what we can do is convert it to lactate, also help recycle NADH back into NAD. It then leaves the muscle and can appear in blood. And indeed, we see this happen with exercise, and if you're in the lab, we're going to actually be taking blood lactate measures here in a few labs in the future in order to actually measure that and see how it changes with exercise. Once that lactate is in the blood, it has several different factors. If we think about this as the Cori cycle, this figure I don't truly love. I'm going to explain a little better. The Cori cycle is truly that this lactate goes from the muscle and the blood into the liver, and the liver then converts it to glucose or glycogen. Converts it to glucose, which then can be converted to glycogen. We can then break that glycogen down into glucose, back into the blood, and we can essentially feed this system. So again, the idea of the Cori cycle is that lactate leaves the muscle, goes to the liver, makes the liver turn it into glucose. The glucose can then be either turned into glycogen or secreted as glucose again, and can then actually be fed back into the muscle to provide a substrate for an energy. The analogy I like to use for this class is if you were in a car and you had some ability to hook on your some type of newfangled device onto your muffler, and so that when you use gasoline, you would have this byproduct of carbon monoxide and gas fumes that would go and travel, normally exit out your muffler, but instead this device on your muffler actually captured it, turned it back into gasoline, and then put it back into your engine, and you could use it again. That's the idea of the Cori cycle, right? Lactate is a byproduct. It's sent out down the muffler, which is the bloodstream. It gets caught in this newfangled device that's yet to be invented. It turns it back into gasoline, and that gasoline then feeds your motor system all over again. It's a pretty neat system. Indeed, we know that the Cori cycle is responsible for about 20% of lactate clearance. And I have some terrible handwriting. Right. So where does most of the other lactate go? So when lactate production is high, what we now know is that the lactate shuttle is really, really important. The lactate shuttle is that once lactate is produced inside a single muscle cell, that lactate then enters the bloodstream, and it can then be used by muscles nearby, the heart, or kidneys. The heart absolutely loves lactate. During high endurance exercise, I mean, it just eats it up, gobbles it up. It takes lactate, turns it back into pyruvate, and then shuttles it through aerobic metabolism. No problems, absolutely loves it. Skeletal muscle can do the same. So when might this be efficient? Again, really high intensity exercises, this can be important because of the type 2 fiber activation, right? We talked about this in the last exam. As we recruit more type 2 motor units, those unfortunately have the problem of having a low mitochondrial density and rely heavily on glycolysis, which means they're going to make a lot of lactate. If you put it close to a type 1 fiber, though, lots of mitochondria rely heavily on anaerobic metabolism, and so that muscle will actually use the lactate produced from the muscle nearby to help clear it. And that is the idea of the lactate shuttle. And we now know during high intensity exercise that that's about 70% of lactate is removed by the lactate shuttles of nearby tissues using lactate, turning it back into pyruvate, and sending it down the aerobic pathway. So let's look at the energy that we can generate from beta oxidation. Again, the idea is that we chop this fatty acid into 2 carbon segments. So I'm going to go ahead and do that now. There's a 2 carbon segment. There's a 2 carbon. So let's now count how many 2 carbon segments we have. 1, 2, 3, 4, 5, 6. So this is a 12 carbon fatty acid, which of course into 2 carbon segments gives me 6 sets of 2. So we can convert each of these 6 sets into acetyl-CoA. The first thing that we have to do, though, to begin beta oxidation is just like in glycolysis step, we need to have some activation energy. It takes 2 ATP per fatty acid in order to activate these molecules in order to do the conversion. Not every single step, that's 2 ATP per fatty acid. So we're going to take 2 at the end of the segment. So each acetyl-CoA that enters the TCA cycle, you remember 3 NADHs, 1 FADH, and an ATP. We can add those all up. That gives us 10 ATP per acetyl-CoA that gets sent in through beta oxidation. Right? If we look, we can send this one in, this one in, this one in, this one in, this one. So we can send all 6 in. So that puts us here. So 6 acetyl-CoA in, 10 ATP. We'll make 60 ATP from sending these carbon segments into acetyl-CoA. Also, in the process of beta oxidation itself, kind of like the conversion of pyruvate into acetyl-CoA, we also produce 1 NADH and 1 FADH in that conversion process. However, you'll notice that's only for the standard looking carbon molecules. So here, this one is a carbon bound to 2 oxygen molecules. Right? So we kind of got to kick that one out of the window. We don't get this energy investment of 1 NADH and 1 FADH. So here, when we calculate the version for the conversion into acetyl-CoA, we only can do it 5 times. So 1, 2, 3, 4, 5. This last one with the carbons bound to the oxygen, we're unable to use that. So here we'll produce 1 NADH and 1 FADH, gives us a total of 2.5 plus 1.5, gives us 4 ATP. Therefore, the conversion step 5 times 1, 2, 3, 4, 5 times 4 gives us 20 ATP. So total from beta oxidation of a 12 carbon fatty acid would give us 100 ATP minus the 2 that we used for the investment phase, giving us a total of 98 ATP. So you can see why fat is a really great way to make a lot of ATP relatively cheaply, and why it is a very good source of ATP during low intensity exercise, and we'll talk about how and why that works, its pros and cons here in the next video. One of the things I'll comment, one thing that you need to know for the exam is you're going to be able to need to know if I give you a certain carbon length fatty acid, you're going to need to be able to convert how many ATP you could get from that. So make sure you understand this slide, can work through it, refer to the book, send me an email, ask some questions. The book has a really nice table laid out that I didn't put in that actually breaks down, each where they come from in the Krebs cycle, whereas I just kind of lumped them all together since we covered that in the last video. So the very last slide is just to kind of show you the coolness of physiology, right? And this may not make any sense whatsoever to you at first, but hopefully, or not, maybe it may be a good deal. But here's an idea: is how efficient is oxidative phosphorylation? In other words, how good are we at converting food into usable energy, right? Here's just some numbers to let you know. I'll just say this. You don't need to memorize these numbers. I think this is just cool physiology. So 1 mole of ATP has an energy yield of about 7.3 kilocalories of energy. We can form 32 moles of ATP from a single mole of glucose, right? So therefore, the potential energy from 1 mole of glucose is essentially 686 kilocalories per mole. So if we do that, what we can do is we can generate 32 moles of ATP per mole of glucose times 7.3 kilocalories a mole divided by 686 potential energy released. Multiply that by 100, and that gives us what we would consider is the efficiency. So how good are we at converting ATP into energy and not wasting it as heat, right? And indeed, we come out to be about 34% efficient. 66% of this process is actually lost as heat. So you can see why when you get cold and you shiver that you're churning ATP in that cross-bridge cycling, turning on oxidative metabolism in order to make ATP, because 2/3 of the energy used or energy stored up in a glucose molecules are actually released as heat and will warm you up. But what does 34% mean? Well, if you're curious, is that a good number or not? Actually, that's a phenomenal number. So most vehicles, I used the gasoline example earlier, most modern vehicle engines are about 20% efficient. And that's actually improved over time. They started out about 15% efficient. Now there's some that reach about 25% efficient. So the idea that your car, when you push on the gas pedal, you actually lose about 80% of the energy contained in the gasoline molecule to move your car, or is actually lost as heat. Only 20% is actually used to move your car forward. whereas the body is much, much better at that, which is pretty phenomenal physiology. So we use about 34% of that energy that we can make ATP that can then use us to move forward. And I think that's just phenomenal and a great way to end the lecture. In the next module, we'll talk about how all this relates to exercise.